Yes. Okay, so if I have a charge Q here, my pointer, here we go, and it's somewhere right here. That's my charge Q. Okay, and then I have some other charges around it. Let's say there's Q1 over here, and Q2 over here, maybe Q3 over here. Then each of these charges can interact with the given charge. Okay, you can think of the Q1 and Q2 and Q3 are source charges, right? And there's an electrical interaction between all those charges. And we can figure out what the energy is. We don't know how to do that yet, but we will. What is the energy interaction between all those particles and the test charge, Q, okay? And if we figure that out, then we can define then the potential at that point to be the energy of that system of particles divided by Q. That's going to be that's the idea here. And you can see this is sort of very analogous to what we did for the electric field, right? For the electric field, we define that to be the ratio of the force on a charge divided by the value of the charge, right? So it's the same concept here. We're sort of looking at what is the energy per unit charge at that point in space where the particle is located. Okay, so some things to note here. So the potential we will see only depends on the geometry. The geometry and the amount of the source charges. Amount of source charges. So it does not depend on the test charge value, obviously, because we're defining that out, but it's worth noting. Charges. In some ways, this new field, right? We think about this now. Remember, we define a field to be some sort of function that describes a quantity throughout space and time. So we could define this throughout all of space. And so we can consider this a scalar field because it's just a number here. Remember, energy is just a number, charge is a number. So V in this case, the potential is going to be a number also. So V, so the potential as a scalar field is somewhat simpler than the corresponding field, which we can also define and calculate. The electric field is simpler than the vector field E. Okay, so in some ways that can be potentially a little bit perhaps easier to work with. We'll see in some cases. And one other advantage of taking this and having, you say, why bother define another field? Well, in some ways then, because it's a scalar field, we'll see that there are different ways, perhaps easier ways, to visualize the potential as opposed to the electric field. An electric field being a vector field, you have to draw vectors at every single point in space. That can be harder. So arguably, it's easier to visualize the potential. And we'll see some methods for doing that here in a bit. Visualize the potential in various ways. Okay, so again, this approach is not better than necessarily the approach of using forces to characterize the system. It's a different approach. It's a different perspective, and we'll see that there are some advantages to it in certain contexts. Okay, there is, of course, whenever you have a unit, a quantity, you have to have a unit to go with that quantity, typically. And in this case, then, we know energy is given in joules in the SI system. We know charge now in this course defined in coulombs. So if you can then take this ratio, 1 joule per coulomb, and that is usually given a special name, it's the volt. Okay, so 1 joule per coulomb is 1 volt. Capital V is the symbol here. and named for Alessandro Volta, one of the early investigators of electrical phenomena. Okay. Any questions about this sort of general definition and introduction here? So we now have a formal definition of the volt. Okay. So now I need to talk a little bit about why this is even possible. So if I'm going to define a field which is everywhere throughout space, I need to have it such that it's uniquely defined, right? It can't have multiple different values at a given point in space. That doesn't really make sense. So in order to do that, we have to demonstrate that the electric force is a conservative force. Okay. So does anybody remember what a conservative force is? No. Okay. Yeah.
The initial amount is the same as the final. Basically 0 in total.
That's kind of on the track, right? So let's maybe refine that a little bit. So the idea then with a conservative force is that if you have some sort of, so let's take another example, like maybe gravity. Gravity is a conservative force. Why is gravity a conservative force? Well, I have an object, okay, and I know that this object at this height above the surface of the Earth has a certain amount of energy, right? I can calculate energy H, and that will give me the energy here. I can also put it up here, and that's also has some additional energy, right? So change in energy between these 2 points, okay? And what the assertion is then is that when you have a conservative force, that the path that you take to go from the initial position to the final position, that is the energy change that you get is independent of the path that you take, right? So I can go from here to here straight up, and that'll give me a certain energy. I can also go like this, that'll give me the same energy. Or I can go like this, that'll give me the same energy. But the path that you take does not matter. Right? Why not? Well, because it only depends on the height that you get to. That's what matters. Right? It doesn't matter how I got to that point. Not every force is like that. So for example, friction, right? Friction, it matters. If I take a shorter path, I'll have less friction than if I have a longer path, I'll have more friction. That matters. The path matters. So the assertion here is that the electric force is in fact more like gravity. It's a conservative force, that the path that you take going from one point, some initial point, to some final point, the energy change is going to be independent of that path. So the sort of qualitative argument, which I'm going to give you here, is as follows. So here we go. We've got here a charge Q1, that's stationary. We have a charge Q2. Charge Q2 is starting at point I. It's moving along a path to point F. Okay. Now, we know how to calculate the force on charge Q2 due to charge Q1. How do I do that? Do you remember? Yes.
Coulomb's law?
Coulomb's law, right? So we know Coulomb's law holds. And we know in particular then that Coulomb's law is always acts, so let's write down Coulomb's law. Coulomb's law says that the force is given by K, Q1, Q2, divided by R squared times R hat, right? Where R hat is this radial unit vector that points from the source charge to the test location. So in this case, let's take this to be the source charge, and this will be my test charge. Okay. So in particular, then, if we go down over here, we can see then that every time no matter where my particle is along this path, I'll get some radial unit vector which will point away from that that particle. You know, if it was over here, it would point like that, right? It's always going to point away from the particle. So over here, point straight away, like this, okay? That's always going to be my radial unit vector, okay? So it's a central, they call this a central force, right? The force always acts from the central point, in this case, the source charge. Okay, so now we know then that the energy that it takes to go from point I to point F, we calculate that's the work done on the particle, right? That's the work kinetic energy theorem. So how do I calculate work? Remind me, how do I calculate work? Yeah, Drew.
Well, that would be the force vector dotted into the distance vector.
Okay, the force into the displacement. Yeah, so we're going to go work here. Work here is going to be equal to force dotted into the displacement. Okay, so in general, we're going to look at what we can do then. If we have a short space, then we can do this. This will be my answer. But here now my force could be changing. You can see that the force direction is going to be changing as I go along this path. So what I have to do then is I have to break up my path into a bunch of little segments like this. Okay. And as I go along those segments, I can calculate the work done along each segment by doing force dotted into displacement, right? Which again, we can always write as the magnitude of the force times the magnitude of the displacement times the cosine of the angle between those two vectors. Okay, so how am I going to do this? Well, what I can do, like I said, I'm going to break this up into some pieces, okay? And but I'm going to go even further than that. I'm going to say, well, I'm going to take. I'm going to have either two choices when I'm taking these steps. I can either go straight, directed along the line radially away from Q1, or I can go tangent to that. Okay? So in this case, I'm going to go up, one step up, and then I'm going to curve, one step curve, one step curve. Okay, and I can do this to at least get an approximate path over which I'm going from point I to point F, right? If I take even smaller steps, I'll get even a better approximation still, right? I can keep doing that, pretty much get as arbitrarily close as I want to the actual curve path. Now, why do I care about going either in a radial way or a tangential way? Well, let's think of it like this. So at each of these points here, let's, for example, let's pick this point right here. This force you can see is going to be radially directed, right, as it should be, away from Q1, okay? And in this case, then, am I going to do work along that displacement path? Well, yes, I am, because you can see here the angle between F and my displacement, which is a little blue line here, line segment. Those are in the same direction. Theta is 0. Cosine of 0 is 1. So I definitely will do some work there. Now, if I'm now going, though, in one of these tangential segments, like this, okay, now the angle between my force vector and my displacement vector is 90 degrees. What is cosine of 90 degrees? 0, right? Okay, so you can see then that I will only do work when I'm going along the radial paths. Anytime I go tangentially, I'll do no work. Work, no work, work, no work, work, no work. All the way from one point to the other. All right, so I can add up all those contributions from all the different radial segments. That will give me my total work from point I to point F. And here's the thing. I can now take, if I were to sort of shift down these radial segments, okay, down to the line which directly connects point I to point F, as shown here. Okay. And now, if I calculate the work along this path, well, these are all radially directed, right? They're all along the line between Q1 and my particle, and these on this line directly. And so I'll do work all the way. There's no intervals when I'm doing no work. And so what we can conclude here is that the work done to take the particle from point I to point F is going to be the same along this path as it would be along this path, right? But this path was arbitrarily chosen. You could have chosen a path from here, you could have chosen a path up here, and I can make the same argument. Right? So the idea is that by any path that I choose, I'm only going to be doing the same amount of work as if I go directly from point I to point F, and therefore the electric force must be a conservative force. Question?
That's true even if the path loops back on itself at some point?
Yeah, because you can always break down any path into these radial and tangential segments. If you, and you take small enough steps, you'll get closer and closer and closer to the same. Other questions here? Okay, so you can be more rigorous about this, but this is the qualitative idea about why the electric force is a conservative force. And this is important because if we have a conservative force, now we can sensibly define a potential function, because it won't matter how we get from one point to the other. Okay, so this is you can show this for the electric force. It's true for any central type force, gravity, electrical force, etc. Okay, so that's the argument there. All right, so next up then, let's try to see if we can actually calculate this potential function and potential energy for a simple scenario, and that's for a uniform field. How do we get a uniform field? Well, I had asserted previously that one way to do that is if you have two really large plates, okay, one of which is positively charged, one of which is negatively charged. In the book, they call this a parallel plate capacitor. We'll talk about what that is a little later. We have a whole chapter on capacitors. But for now, what we just need to know is that if we have two really big plates, oppositely charged, we'll get a nice uniform field. We have the same charge in each plate, the amount of charge. Okay, so here's what we're going to do. I'm going to go in and we're going to consider two states here. We'll have an initial state and a final state. Okay, and you can just think of this as one small segment of a large system. And so in the initial state, I'm going to have a particle, and the particle is going to be right here, and it'll be at I'm going to define a coordinate system where my coordinate on the vertical axis is 0 at the negative plate, and I'll have some coordinate s sub I, my initial coordinate, at the location of the particle. Okay, the charged particle. Let's make it a positive charged particle. In the final state, the particle will have moved down to a new position. Let's call it s sub f. Here's my particle here. Here again, s equals 0 at the negative plate. Right, so what we'd like to do then is, can we calculate the work done on that that you need to do on that particle to move it from the initial position to the final position? That's our goal. Okay, so let's sketch in the field here. Which way should the field be? Yeah, Zachary.
The positive charges going down to the negative charges.
Yeah, exactly. We always know field goes from positive to negative, right? So, and it's a nice uniform field, so I'm going to draw some lines, just draw some field lines like this in my space, just to remind me that this is a nice uniform field. Okay. Okay. Great. All right, so now let's go ahead and see if we can calculate the work done here to move that particle. All right, so we know work, we just talked about this, the work is going to be defined as the force, electric force, dotted into the displacement. And in fact, we need to integrate from the initial position to the final position. Essentially, if we think about breaking up this path into a bunch of little pieces, we're going to add all those up to get me from this initial position to the final position, okay? All right, in this case, now, because my field here is uniform, that means my force, which is some charge Q, that force will also be uniform, right? Because if E is, force is equal to the charge times the field, if we go to chapter 2, that means the force is also going to be constant, right? One of the advantages of being in a uniform field. Okay, if that's the case, then that means I can pull out the force here, and as a result, I'll just be integrating from s sub I to s sub f over ds. Well, that's just the distance between those 2 points, right? So essentially what I'll get is the force then dotted into just this displacement, delta s, right? Or this is really equal to the vector from going from initial position to the final position. So s sub f is essentially that delta s. Okay. All All right, so let's go ahead and put in our expression here. This is going to be then equal to QE dotted into delta S, okay? I'm now going to use the definition of the dot product. So Q is going to be the magnitude of E times the magnitude of delta S times the cosine of the angle between those two vectors. Well, what is the angle between E and delta S? Yeah,
Negative 90 degrees, which
well, the angle between E and delta S. So E is the blue vectors. Delta S is the black vector. So
then it'd be 0.
it would be 0, right? Yeah, right. They're parallel, right? We're going in the same direction as the field. Okay, so here then cosine of 0 degrees, right? All right, well, cosine of 0 degrees is 1. Okay, so that's just going to essentially go away. And what we'll get then is Q, magnitude of E, and then the magnitude of delta S. In this case, S sub I is bigger than S sub F. We know this has to be a positive value, so we're going to be S sub I minus S sub F. Okay? And if we go then and distribute this through, we'll get Q magnitude of E, S sub I, minus Q magnitude of E, S sub F. So this then is the work that we have to do to move that particle from the initial position to the final position. Okay. However, what I really want to do is I want to relate this to the potential energy. That's really what I want to calculate here, because potential energy is related to potential. So how do I relate this to potential energy? Well, I know from the work kinetic energy theorem, which we talked about earlier this week, that the work done on the particle is going to be the change equal to the change in the kinetic energy, right? We also know from energy conservation, okay, that the change in the kinetic energy is equal to minus the change in the potential energy, right? That's what we talked about last time. And so if I put these together, we see the work done is going to be minus the change in the potential energy. Okay. Again, whenever we use the delta, we mean it's going to be the final value minus the initial value of that quantity. And so if we distribute the negative sign through, that's going to be U sub I minus U sub F. The work done is the initial potential energy minus the final potential energy. Okay, but this work has to be the same as this work, right? There's only one work. So what can we conclude? Well, these two things must be equal, right? They're both work, the work done. And so if I write it kind of right under one each other like this, right? What do we see? Well, these quantities must be equal, right? So in fact, we can then see that the potential energy, okay, so the potential energy U, is going to be equal to, in general, the potential energy function as a function of position S, okay, is going to be the Q magnitude of E times S. And technically speaking, we can also add in a constant here, okay? A couple ways you can see that. First of all, because we're taking a difference here, right? If I take U sub I minus U sub F, that constant will cancel out, right? So that's one way to look at it. The other thing is too is I kind of glossed over this, but when you do an integral, right? There's always that sort of plus C, right? You can always add a constant. That's essentially what that is. So in other words, you may recall from internal mechanics, it's really the absolute value of the energy doesn't really matter. It's always changes in energy which are physically meaningful. Okay, so we can always shift our energy by constant. That's not going to change the physics. I should note here, this assumes that S equals 0 at the negative plate, right? If you put your 0 somewhere else, you might get a different result. But we're going to pretty much assume that S equals 0 at the negative plate for this result. Okay, so that's our potential energy that we've gained or lost here in this system. that as we move the charge, okay? We can also then go ahead and define the potential function here for a uniform field. And that's going to be the the V, the potential function is going to be U divided by Q, right? So in this case, then that's going to essentially just give us then magnitude of E times S plus some other constant, let's call it V naught, which would be essentially U naught over Q. So the takeaway here is that both the potential energy function and the potential function are linearly dependent on the position from the negative plane. Fairly simple functions are linearly dependent functions. Okay. Any questions here? It's our first sort of result. Okay. All right. Well, let's see then how this, how we can sort of visualize and use this. Before we do that, I want to remind you about something back from energy mechanics as well. So, energy diagrams. Anybody remember energy diagrams? What was that? Okay. Just as a refresher. Suppose I have some object, some ball or an object, and I take it and it's on the ground and I give it a kick and it goes up in the air, right? We can make a picture of how the energy changes in that system, right? So how do we do that? Well, we usually plot the energy on the vertical axis and then some position coordinate on the horizontal axis. In this case, this is the distance above the ground. So the ground is at y equals 0. So initially then, if we have some initial kick here to my my particle, it's going to have some initial velocity v, which means it's going to have some kinetic energy. How do we calculate kinetic energy? Remind me. Kinetic energy. All right. So we'll order this down. 1/2 mv squared. Does that sound familiar? Kinetic energy. Okay. K 1/2 mv squared. Okay. So it's got some velocity, right? So that means I'm going to have some kinetic energy. On that, the ground, and in this case, that means I have 0 potential energy. So all my energy in the system is energy of motion. However, so in other words, we can plot this out, right? So we know that the potential function for gravitational potential is y mdh or mgy, right? In this case, right? So that's going to be the function here. That's the potential energy function. That's u. Okay. In this case, then I have a certain total energy in my system. In this case, it's all potential or kinetic energy to start with. That's the brown line. Okay. So we're down over here. We have a certain amount of difference between our energy and our potential energy. Now, as the particle goes up, right, it starts to go up this hill, if you like, in the energy space. It's at a higher altitude, and as a result, then it's gained some potential energy. But because energy is conserved, it's lost some kinetic energy. You can see the total is the same. We've now divided up between the kinetic energy and the potential energy. Eventually, right up here, right, the ball reaches a maximum value, maximum height. That's where all the energy now is potential energy. There's no kinetic energy left. That's given a special name. It's called the turning point, right? Why? Because that's the point at which particle turns around, comes to fall back down. All the energy is potential energy. It then starts to fall again, essentially going downhill in the energy space. It gets more kinetic energy, and eventually will hit the ground with completely all kinetic energy again. No potential energy. Just coming back a little bit, familiar a little bit? All right, so another way to look at these systems. Okay, so can we do something similar here for our electrical system? I think we can. So we're going to do sort of comparison. Let's start off here with a positive test charge in between the plates of our capacitor. can you go ahead and sketch out for me what you think the potential energy function will look like as a function of position? Again, we're taking S equals 0 at the negative plate over here, okay? And then what the potential function will look like, just for the positive charge. Do that right now. Okay, get your potential energy function and the potential function as a function of position from the negative plate, based on what we know. Look at the expressions we had derived. See if you can plot that out. Yeah, question?
Why don't we use R for like the position?
Well, this isn't really a kind of a radial system, right? It's not spherically symmetric. You could use Y or X or anything else. I just chose S as an example. You could use R2, but it's just people think about R in spherical coordinate systems. Okay, how are we doing here? You get some graphs put down. How many people have a graph? Okay, give me another minute or two. Just for the positive charge. Okay. Anybody want to share out what they did for the potential energy as a function of position? What does your graph look like? What function are we graphing here? Let's go back. Right? This function we're graphing, right? This is the one we're graphing. This is the exact same situation, just going to rotate it. Okay, so that's the function we're graphing. Okay, so let's write that down. So in this case, U of S was equal to Q E S plus U naught. Okay. Now you can always choose the constant whatever you want. So I'm going to go ahead and choose constant to be 0. In that case, then, what will my graph look like? Scott?
The electric field will get stronger the closer you get to the positive side. The liquid is repelled more strongly, so it'll be inverse square, right?
Not inverse square, no. Yes, go ahead.
So just a quick question for
Yeah.
clarification.
Yeah.
If we plot a negative line, would that mean we're going towards 0? Because if so, the potential energy would be stronger in the negative direction the closer we get to the positive plate.
Okay, so so positive or negative depends on the energy, right? So we want to look at our function here. So Q is positive, right? Magnitude of E is positive. Right. So S here, we're starting at 0, and it's going from 0 to some positive value. Okay. So in this case, is our energy positive or negative? That'd be positive, right? Everything here is positive, positive, positive. Okay. So in this case, function, the energy is always positive. What does the graph look like? Yeah.
Basically, y equals mx plus b going straight upwards towards the right.
Okay. Yeah. So we'll get a linear function. We should have a line, right? So this is a like he mentioned this y, and that's essentially m, x, and plus b, but I'm set u equals 0. So in this case, then yeah, I'll start here at 0, and I'm going to go up like this, like that, like this, and my slope here will be, slope here will be QE. Okay, that's what we get, linear function. All right, that's the potential energy. What about the potential? What will that look like? What function are we graphing there? Remember? Can you go back a couple slides? Okay. That was my function. That's the potential energy, potential function for this uniform field, which is what we have. Okay, so let's write that down. V of S here is equal to E S plus potentially V equals 0, or V naught. I'm just going to set that equal to 0. So if I set that equal to 0, what kind of function will I get here? What will it look like?
Another y equals mx plus b. This time the slope is the electric field strength.
Okay, yeah, so it'll be still linear, maybe different slope, right? So I'll just maybe draw it this way, something like that. Now my slope could be different depending on whatever Q was, but it's going to be the magnitude of the field. Okay, so that's how we would characterize these graphically. It's just a way to visualize the change in potential energy and the potential. If U naught or V naught were not 0, it would just be offset. All right. Any questions there about the positive test charge case? All right. Next thing is then, how are things the same or different if I have a negative test charge? Okay, so see if you can plot out the same thing here, U versus S, V versus S for the negative test charge case. I'll give you a moment to do that. Okay. What'd you come up with here? What about the potential energy function? It's a function position here. What's your graph look like? Yeah.
Still be a linear function, but with a negative slope.
Okay. A linear function, but with a negative slope. Yeah. So in this case, now Q is negative, right? E is still positive. That's positive. So this will be negative, right? And so it'll start off at 0. If I say U naught equals 0, and it'll come down like this, right? So here now my slope is, so we say this is Q naught. This is plus Q naught, and this is minus Q naught. This will be minus Q naught times E, right? So yeah, negative slope. What about my potential function? What's that going to look like? Yeah, Drew.
The velocity rev would be identical to the positive one here, to it being independent of charge.
Ah, okay. Yeah. So in this case here, we say it does not depend on charge. There's no here. So this is still positive, this is positive. So yeah, we're still going to look pretty much identically the same. Yeah. And that's kind of the point of the potential function. It's independent of the charge that you'd put at a given point. That's the whole idea. Right? So what is creating the potential is not the charge, it's the plates, right? And the plates haven't changed. So the potential function should be the same. Okay? The potential energy changes though, because now we're looking at the interaction between the plates and the charge. Okay? And the charge has changed. What else do I want to point out here? A few things. So first of all, does this make sense, right? So in general, right, most of the time, systems will tend towards lower energy, right? If I take an object here, right, why does it go down? Because it's lower energy down here, right? Closer to the surface of the earth. So in this case, then, if I drop a particle here, positive charge, which way is it going to go? Point in the direction it's going to go. String graph. Which direction is the positive charge? If I let go right here, which way is it going to go? Should go to the left, right? That's lower energy, right? It's also going to go to the left from our previous perspective, right? From the force perspective, we'll have a force to the left, right? And therefore it's attracted to the negative. So that's the force perspective. This is the energy perspective. It's going to lower potential energy. Just like the ball when you drop it. Okay. What about over here? If I take a negative charge, I have it, put it right here and I let it go, which way is it going to go? Take your finger and point in that direction. Yeah, everyone's pointing the other way. Yeah, sure. It's going to go to lower energy, right? In this case, lower energy is towards the positive plate, right? We'll have a force in this case to the right, which is going to attract it to the positive plate. Right? So the energy diagrams are consistent with the force perspective, right? As it should be. Right? Okay, so systems tend toward lower energy. There's then one thing we have to be kind of careful with then. If we look then at positive charges tend toward lower potential, right? Because lower potential corresponds to lower potential energy. However, negative charges tend towards higher potential because higher potential, when you multiply times that negative value, goes to lower potential energy. So that's one sort of thing you just have to remember. Even though these potential functions are the same, the way the charges will respond, if you just all you knew was the potential, you have to remember the negative charge is going to go to higher potential because that's lower potential energy. Okay? Does that make sense? Thumbs up, thumbs down. Thumbs up? Okay. All right. So just our sort of first foray here, and then just sort of visualizing and graphing potential functions. Any questions here? Okay. Oh, one other thing I want to mention. So if we look here at our, if we had some sort of spacing between the plates, let's call that D, okay? Well, then if I look at my function here, right? So we would say then the change in potential across those plates is given by the magnitude of the field times D, right? The spacing between the plates. If I move the particle all the way from one side to the other. And so if we just look at the dimensions here, so on the left-hand side we have volts. Here we have oh, sorry, let me do it this way. I can solve then for the electric field, okay? Electric field is going to be the change in the voltage over the distance, right? So if I look at the units here, that's going to be volts per meter, okay? So this is an alternative way we can do units for the electric field. Previously, we used newtons per coulomb. Here, volts per meter. They're actually the same. So 1 Newton per coulomb is 1 volt per meter. So you may also see this written out in some books. They use them interchangeably. Okay, so 1 Newton per coulomb is equal to 1 volt per meter. So I encourage you to prove that to yourself, but that's true. All right. With that, then I want to move on to the next thing. Let's switch to the next thing. That's a question. Okay, so let's try out this one here. I have an electron. It's moving from point I to point F. It's in between two large parallel, charged parallel plates in a capacitor situation. What is the change in the electric potential energy? Is it positive? Is it negative? Is it zero? Or is there not enough information to say about the change in the potential energy? Okay, again, electron moving from point I to point F. What is the change in electric potential? Okay, let's do a poll here. See what you're thinking at this point. Please vote now. Cards out. So I'm saying, come get me some. Get your plate later on. So yeah, okay. So got a kind of mix of A's and B's. Looks like A's and B's. So not really a consensus here. But let's work this one through. See if we can figure it out. So in this case, we know the potential energy is going to be given by Q, E, S, right? Or again, we say S is 0 at the negative plate, according to our previous derivation. All right, so what do I want to calculate here? I want to know the change in electric potential, and the change is always the final minus the initial, right? Okay, so let's go in, plug in some things. So we start out here at some position S sub I. We end up over here at some position S sub F, right? So if we now plug in with our expression here, we'll have Q E S sub F minus Q E S sub I, right? Now in this case, Q, what is Q? We said Q is negative, right? It's negative E, right? It's our electron. So let's put that in there too. So we'll have negative E, capital E, S sub F, and then minus negative E, capital E, S sub I, right? And so if I multiply the negative times negative is positive, and rearrange things here, I'll have E, capital E, S sub I, it's now the positive term, minus the E, capital E, S sub F. Right? All right, so all we have to then do is, at this point, which one of these is bigger? Right? Because that'll tell us whether it's positive or negative. Yeah? So which one is bigger? The first term or the second term?
The S of I term.
S sub I term. Yeah, S sub I term, yeah, because E is positive, capital E is positive, that's actually right. So it really depends on just the values of S here. Now, you can see from our graph, S is 0 at the negative plate, so S sub I is bigger. So the first term is larger, right, than the second term, which is smaller. And so as a result, then, this has got to be positive. Does everybody see that? You could also think about graphing it out, right? If you were to graph this out, U is a function of S, right? We said that from our previous discussion that should get back to the graph that looks like this, yeah? So if I start here at some S sub I, okay, and I go over here to some S sub F, right? Going uphill in my energy space, okay? I'm going to be gaining potential energy. So a couple different ways you could solve that problem. Any questions about this one? Okay, just kind of get you thinking about energy here a little bit. Yeah, and then perhaps one more thing I'll say. You know, if I had an electron here and I let it go, which way is it going to go by itself? Yeah, it's going to go to the right. Yeah, that's a lower potential energy. So if I'm going to move it from I to F, I'm going to have to apply a force to make that happen. Right? So I have to do work on the particle, and that means I'm going to get a change, positive change in potential energy. Another way to look at it. Okay, I want to talk a little bit more about visualization. I mentioned that there are different ways you can visualize potential. It's a little bit easier to think about perhaps in an electric field because it's just a number. Could be positive, could be negative, it's just a number. So here we've already talked about the potential graph, so that's one way. Potential as a function of position. That's our linear function for the parallel plate system. But we can think about it also a different way. So, you know, this system is really, it's a three-dimensional system. We have these two-dimensional plates separated by some distance. And so another way to do this is to say, well, let's look at a particular distance. Let's find all the points at that particular distance. In this case, if I'm 1 millimeter away, my voltage should be 1/2 volt. Right? So I can draw a surface at all the points which are 1 millimeter away. Well, that's a plane. Right? All the points that are 1 millimeter away from this plate is a plane. And now all those points will have a potential of 1/2 volt because they're all 1 millimeter away. If I go to 2 millimeters away, what are all the points that are 2 millimeters away? That's another plane, okay? And at that distance, I'll be at 1 volt. So all these points are 1 volt. These are called equipotential surfaces, okay? And that's down here, equipotential surface. That means they're equal potential everywhere on that, in that plane. And there's a whole set of these. You could do one for 1/2, 3/4, 1 1/4, etc. Bunch of parallel plates. Okay, so you should know what an equipotential surface is, and that's one example. We'll see some other examples later. Now, if you're not a great artist, it may be a little hard to draw this, right? So is there maybe a simpler way to do this? Well, yeah, one way you can think about doing it is maybe doing a cut through, right? Just kind of cut through this here, like that, and draw sort of a, or maybe look at it from a top view, right? The same kind of idea. And that's what's sometimes called a contour map. So now we're essentially looking down on the system. Here's my negative plate, here's my positive plate. Here now are my equipotential surfaces. Well, I'm only looking at the top of them, so they turn into lines. Okay. And this one is 1/2 volt. All these points are 1/2 volt. This one's 1 volt. These points are 1 volt. Okay. It's called a contour map because these then are called contours. And they're analogous to a topographical map. Anybody ever seen a topographical map? They're used to sort of show how hilly something is. So for example, if you had a hill like this, you might draw sort of concentric circles around that in a topographical map situation like this, where this would be the highest, this would be the lowest. So it's the same idea here, right? So that's the contour map. And then finally, there's sort of a little bit of a hybrid one you'll sometimes see called the elevation graph. Not as perhaps as often, but it's kind of a mixture of the two. So in this case, you can see here every at 1/2 volt, I'm at 1/2 volt here at 1 millimeter, I'm at 1 volt at 2 millimeters. And so it allows you to sort of see both the contours, essentially going up in a two-dimensional way, but then also you see the linear function here from the potential. Okay, so it's a little bit of both. Okay, so just going to give you exposure to some different ways you may see in books and textbook and elsewhere about how to visualize the field, potential field. Questions about any of these? Okay, great. All right. Well, let's try a little example then. So I have an electron. I put it here at the black dot. Okay, it's in the given contour map. Afterwards, what happens to the electron? Okay, so again, I drop the electron right here, and now I let it go. What happens? Does it remain at the dot? Does it move upward with steady speed, downward with increasing speed, or sorry, upward with increasing speed, downward with steady speed, or downward with increasing speed? What do you think is going to happen here? Let's do a poll here. See what you're thinking. Please vote now. What's going to happen to my electron when I let it go? And then A's, B's, C's, D's, and E's. One second. Okay, lots of different answers here. All right. Well, let's see if we can figure out this problem. So I'm going to draw a little line right here, okay? And I'm going to plot out what is the potential along that line. Okay, so here we go. I'm at 100 volts, and then I'm at 200 volts, and now I'm at 300 volts. So I'm essentially going to get a linear change in the potential, right? This looks like a lot like a uniform field. And so here I am. Here's my electron, starts off here, okay? And what's going to happen to it? Well, if this is potential as a function of position, what does that imply about my potential energy graph? How do I calculate the potential energy? Yeah.
Because the charge is negative, it'll be a negative slope.
Okay, we said negative slope, right? So maybe it'll look like this, okay? And here's my electron. Okay, so from this perspective then, which way will my electron go? To the right or to the left? It should go to the right, yeah? It should go to lower energy, right? So again, lower energy corresponds to higher potential. So we expect the particle should go upwards, okay? So that means that we're going to eliminate A and D and E. And the question is, does it go with a steady speed or an increasing speed? Yeah.
Steady, because since we're linear, we have to go up by a certain slope.
Okay, so not quite. So here, remember what is our energy that corresponds to energy of motion? Yeah, kinetic energy, right? And so in this case, we'll have our system may have some total energy. Maybe it's right here. Okay, maybe that's my total energy system. So as I go, as I go to lower energy, right, lower potential energy, the difference between those two, again, the difference between those two is the kinetic energy, right? So as I lose potential energy, I gain kinetic energy, right, because energy is conserved. So I'll be gaining kinetic energy, which means I'll be increasing my speed. Does that make sense? Okay. Yeah. So that eliminates D. We're at C here. That should be the answer. Okay? All right, so we can get a lot from these contour maps, right? You get a lot of information about what's happening with the particle. All right, we'll stop there. We'll pick up next time. I'll start talking about potential of point charges. See you on Monday. You can just drop your folders up here.
After taking the test, I feel this as well as I've been going to tutoring sessions and some class sessions. Is there any other ways that you're running classes? I mean, so I think something that you might be able to figure
Let me take a look at the test first, and figure out what the issue would be, okay? And go from there. So, yeah, happy to meet with you. Like I said, I have student hours after this class on Thursdays. I have them in the afternoon on Mondays. So those you can know I'm in my office, but we can actually.
Yeah, student hours are going to be very great for me because I have classes immediately following common hour.
Yeah, well, I do it during the common hour. Yeah, so that's fine.
Okay.
Everyone should do that. Yeah, okay. So it's great. Yeah, sure.
You go up the counter.
I was wondering if you can explain to me how I was supposed to do the last two problems on the test. I wasn't really sure how to do that. I was looking through, I might have missed it in the notes or in homework. I'm not sure where I'm supposed to learn how to do that. The last two questions. Is that something you can share with me right now? Or is that something?
Maybe let's postpone that a little bit because I still
Yeah,
have people to do quick tests and such and such.
Yeah.
I don't think people want to do it today.
So, yeah, well, we can definitely talk about that,
Okay.
next week. and then
Yeah.
next week. Yeah. Is that your stuff right there, or is that?
Oh, there you go.
Sure.
Can you explain how it was negative to get positive? Because I understood how the kinetic is increasing. That makes sense because you're going to the right direction. So it has to move with certain speed, not steady because it's not sure why it's steady, but it was positive. I knew half of it, but
Mhm.
half of it isn't good.
Okay, so the logic is as follows. So I'm along this line here, and I've plotted out the potential. So the potential is increasing as we go up, right? So an increasing potential, because Q is negative, corresponds to a lower potential energy. So energy is lower up here,
Oh,
higher up here,
okay.
because remember, it's Q times E, right?
Yeah.
So as is, and it's being, Q is negative, right? So higher potential corresponds to lower energy.
Okay.
So lower energy state up here, particle is going to tend towards lower energy, so it's going to go upwards.
Okay.
But then as it goes upwards, because its potential energy is now dropping,
Mm-hmm.
the kinetic energy has to increase because the total energy is constant,
Yeah.
and therefore it's got to be speeding up.
Okay.
That's the logic.
It does help.
Make sense?
Yes.
Okay.
Thank you.
Great. Super. Got to shift your brain a little bit to think about energy.
Yeah.
I've been thinking about forces a lot lately, so trying to get you recalibrated here.
I was understanding why it was going up, but I wasn't sure. I understood it was going up, but I'm not sure why it was doing that.
Right.
So negative charges, you have to wrap your head around that because it's a little different than what we're used to. Like everything in gravity,
Mass is always positive, right? We don't have negative mass,
No.
so we have a hard time thinking about it.